All right, so hi everyone, welcome back. A very good evening to you all. Myself Ayush Tripathi, and welcome you all to this post analysis discussion of the last weekly contest 206. And I hope you have enjoyed all the problem. All the problems were really nice, and I personally categorized this entire contest from easy to a medium level. All the problems were doable, and don't worry, we'll discuss the solution for all the four problems. So before starting the discussion, I need a quick confirmation from everyone. Write a quick +1 if I am audible. And we'll take this session on off camera. So yes, everything seems good to me. So let's start with the first problem. Maximum matching pair. So in this problem, you are given two arrays ARR and BRR of equal length. You can form a matching pair by selecting one element from each array, but only under the following condition. That is, one element must be negative and the other must be non-negative. That is, one negative element can be paired up with a positive element only. And the absolute value of the negative element must be greater than the absolute value of a positive element. And each element can be paired in at most one pair. And here we need to maximize the number of such valid pair possible that can be formed with these two arrays. So coming to the first example, we'll come to the second problem, which is a divisible and divisible problem just right after this. So kindly wait for the next problem, Kunal. So now coming to the first example. So for the first example, we have array ARR, which is equals to -1, 2, then -3 and 4. Then array BRR, so it is equals to 1, then -2, then 3 and -4. So here it is clearly mentioned that one can only pair a negative element and a positive element. The absolute value of a negative element must be greater than the positive element. So here what I can do, I can form a pair. I can take these two elements. There's a -1, and this with this -1 we cannot form any pair. Then with this +2, I can form a pair with the -4. So one pair I can form, that is a 2 comma -4. Right? That is -4 from the second array BRR and 2 from the first array ARR. Then I can form a pair with the -3. So -3 from ARR and element 1 from BRR. Then I can form a pair. I don't think we can form any other pair. Yes. So in total we can form only two pairs. So my answer will be 2. So yes, 3 comma -1. You can also say 3 comma -3 comma 1. And here we can have 2 comma -4. So the expected output is number of pair. So we cannot solve this problem with the brute force. It is not possible to iterate over all the combination, all the possible pair, because the value of n can be up to 10 power 5. So if you check for all the possibility, then the time complexity would be order of n square, where n is the size of the array, 10 power 5. It is not possible. So we have to do something better. So let just first draw some observation. So the very first thing, we always try to pair a negative element with the positive element which has the maximum value. And in this way, we can maximize the number of pair, right? For example, let's say you have your ARR and it is equals to -3, and let's say then we have a -5. Then let's say at here you have a element 4, and at here let's say you have a element 2. This is my array BRR. Or instead of okay, let's keep the element with the value 2 only. So one thing what you can do, if you form a pair of a -5 comma 2, then it is not the best idea, because you cannot pair this a -3 and 4, right? So this is a greedy problem, completely greedy problem. With every negative element, we always try to select the element with the maximum value, so that we can open more possibility for the future. And in this way, we maximize the number of pair. So this is not the correct answer. The correct way is to form a pair -5 comma 4, and then now you can form a pair -3 comma 2, right? So yeah, this is the complete intuition how we come to the solution. So the first step. So let me write the steps over here. So the very first step is to sort the array, sort both the array, sort ARR, and then sort the second array, BRR, right? And after sorting, iterate over all the elements of ARR first and consider only the negative element. So for every negative element in this array ARR, I'm going to select the element with the maximum positive value and it valid. So basically what I can say, I can use a 2-pointer technique. So use 2-pointer. And the idea for the 2-pointer, for every element, for every ARR of I which is less than 0, at this point of time, I'm not going to consider the positive element. We'll come to this very soon, that how you can consider the positive element. So for every ARR of I which is less than ARR of j, sorry, which is less than 0, that is a negative number, find maximum value. Find the maximum value of BRR of j. Such that this BRR of j is greater than 0, that is a positive number, and its absolute value is less than the absolute value of a negative number. Such that BRR of j is greater than 0 and the absolute value of ARR of I, this should be greater than BRR of j, right? And how we can find the maximum value? So for this purpose only, we have we shorted both the array. we sorted both the array just to find the maximum value which is valid, maximum value of a BR of J which is valid. So we can use a two pointer. So we can initialize our first pointer, that is a first pointer I with 0, and this is for array ARR, and then I can initialize the second pointer with the last element, that is n minus 1, right? And in this way we can solve the problem. So but at this point of time I only consider the negative element of ARR. It might be possible when we have a pair from a negative element of a BRR with the positive element of ARR. So yes, it is also possible. So after this swap both the array. So swap ARR, swap ARR of I, and BRR of J. And after swapping these two after swapping these two arrays, it is not actually a particular value but the entire array. After swapping these two array, just simply repeat all the three steps. No, not only the three step, but this third step. Apply the two pointer again. So after this, simply repeat. Now this is the complete explanation from my end. Now let me show you the implementation. But what I would suggest, just pause the video and try to implement it by your own. So this is the method that you need to complete. I sorted both the array, and then here I am having the helper function solve, and it will take a two array ARR and BRR, and we are going to consider all the negative element of ARR, and will form a pair, right? So here I call the function ARR comma BRR, and then I will swap both the array, or I can say I will call the function BRR comma ARR. So these are my two pointer with a 0 and n minus 1, initializing the answer with 0. Then while we are within the boundary, if it is a valid pair, that is element is negative and BRR of J is positive, and the absolute difference of a negative element is greater than the absolute difference of a positive element, then it is a valid pair. Increment your answer and update the pointer. But if it is not the case, that is the maximum value is greater than the absolute value of a negative element, so it is not valid. So in that case we have to discard this positive element, because even it is not possible to pair this positive element with any other negative element in the future also. So that's why simply minus minus. Otherwise we can break the loop. We do not have any other pair. Cool. And finally I'm going to return the answer. The time complexity would be n log of n base 2 because of this sorting. And this solve function will take linear time. Now coming to the second problem. Next divisible element. So you are given an integer array ARR, and you need to find the next divisible element for each element in ARR. And the next divisible element for an element ARR of I is the first element ARR of J, such that the index of J is greater than I, and this element ARR of J is completely divisible by ARR of I. And if no such element exists, then in that case you have to return minus 1 for that position. So coming to the first example, where we have the integers from 1 to 5. So 1, 2, 3, 4, and 5. So now what will be my answer array? So for the index 0, for the first element, the next element which is divisible by 1 is 2, because all the integers are divisible by 2. And you don't need to worry about the 0 wala case. It is not possible to have any element with the value 0. All the elements are positive only. So for this element 1, the next divisible element is 2. Now for this 2, 3 is not divisible by 2, but yes, 4 is divisible by 2. So in this case, the next divisible element is 4. Now for this the 3, 4 is not divisible, 5 is not divisible, so minus 1. Then for this 4, again minus 1, 5 is not divisible. For this 5 also, minus 1. So this will be my answer array. Same as the expected output. Now how we can solve this problem? So again, if you try to solve this problem with the brute force, then the time complexity would be n square, and this will give you a TLE. So how we can solve this problem? And actually, this is based on a very popular upper bound, I can say. You need to know the number of divisor of any number. Upper bound for the number of divisor. Here the value of element can be up to 10 power 5. So the value of n can be up to 10 power 5, right? And each element value is not more than 10 power 5. Cool. Now, to solve this problem, you need to know the very interesting fact, that is a number of a divisor of any number which is less than 10 power 5 is not more than 128. It would be somewhere around 128. So just to be on the safer side, we can consider 128 as the upper bound. But actual count will be less than 128. So this is not exactly the observation, but this is some kind of a fact, or I can say a well-known fact that you need to know. So number of integer, or I can say number of divisor, count of number of divisors. For any integer, which is less than or equals to 10 power 5, is around 128. Count of number of divisor for any integer which is less than or equals to 10 power 5, this would be around 128. So 128 is the like kind of a upper bound. And how I come to this upper bound? So for this, you can read one of the blog on a code forces. So I can suggest you this blog. So let me just paste this link in the chat box. Otherwise, what you can do, just simply search a code forces blog amount of divisor of n, and you will redirect it to this blog. And here someone has mentioned that roughly range that we need to consider is n power 1 by 3. That is a cube root of n that we generally consider while solving the problem. So it is a on and about a 2-digit number. So that's why, just to be on the safer side, 120 is like more than the upper bound. So if you know this fact, then this is a cakewalk problem for you. Just simply iterate over all the integer and find all the divisor, right? And how we can do this thing with the help of a simple for loop. For every integer, I'll iterate over all its multiple, right? So create one map, or I can say one map, and for every integer, store all its divisor, right? So what I can do, I can also create an array, but let's yeah. In my implementation, I have created a map, but you can also create an array. So the maximum element that we would have is like a 10 power 5, right? The value of ARR of I, and simply iterate over all the integer, and for every integer, find all its divisor, right? So iterate over all the integer from 1 to 10 power 5. Then iterate over all the multiples of I. So for every multiple j, so the value of j would start with I, and this is very similar to the sieve of Eratosthenes. I hope you all know about the sieve of Eratosthenes, which we use to find the prime sieve. So I iterate over all the multiple of integer I. So the first multiple is I itself, and then up to 10 power 5. So let me write the complete condition for this second for loop. So while j is less than or equals to 10 power 5, because if any multiple which is greater than 10 power 5, then we don't have to consider. And every time we increment the value of j by I. So j is equals to j plus I. That is take me to the next multiple. So in the first iteration, the multiple is I. In the second iteration, the multiple is 2i, 3i, 4i, 5i, and so on. We iterate over all the multiple. And then I can create a 2D array. So multiple of, not exactly the multiple, but I can say divisor. So let's name this array divisor, and this is a 2D array. So this a div of j is a vector. So in this vector, or I can say in this list, we are going to simply add. So let's name this method as add. But if you are a C++ user, then we all know it is a pushback in case of a vector. So simply add integer I. That is, we have a divisor I for the integer j. Cool. And after this, what you can do, this is the first step. And the time complexity for this, let us quickly also derive the time complexity. So in this case, the time complexity would be n by 2, or I can say, actually you don't have to start with 1, you can start with a 2 also. Yes, we can start with 1, because 1 is also a divisor of every integer. So n by 2, simply n, not n by 2, but I can say n by 1. Then n by 2, then plus n by 3, then plus n by 4, and so on, right? So if I take this integer as a common, if I take this integer n common, then it would be 1 plus 1 by 2 plus 1 by 3 and 1 by 4 and so on. So this is nothing, but it is a harmonic sum. Harmonic sum of it is a harmonic sum for which the upper bound is log of n base 2. So that's why the overall time complexity would be n multiplied by log of n base 2. This is an harmonic sum of this is a harmonic sum of first an integer. Cool. So for this pre-computation take log n multiplied by log of n base 2 time. And after this pre-computation, what I can do, I can simply iterate over all the integer. But since we are interested in the next divisible element, so we start iterating from right to left, because for every element, for every integer I must have some information from the right hand side. So for this thing, I will iterate over all the integer from right to left. N minus 1 till 0, right? And for every index, now I'm going to find the answer. So to find the answer, what I can do, I can use a map. Now this time I can use a map. If you are using Java, then you can use a tree map or hash map, whatever you call. So let's use a map, and this map would be of integer comma integer. And let's call this as in my implementation what I have mentioned. Let me just use the same name here. So this is my array fact, but which I have explained with the help of a div. And here it is nd, next divisible. So yeah, I named this map as nd. So this map nd will simply store this map will store a key value pair. So the key will be the element value, and the value will be next divisible element. So before reaching to index I process all the indexes from right to left, and I already have the information. I already have the information from I plus 1 onward, right? So just simply check whether you have the same value or not. So what I can say, if nd of arr of I. So basically, if this key is present in my map, if this key is present in my map, then what I can say, my answer will be answer of I. It is simply equals to whatever the value present corresponding to this key. So nd of arr of I. Because this is a key value pair, and here the key will just simply store the element value. It will simply store the multiple, and this value will simply store the element. So this will store the multiple, and the value will store the element, right? And after this, I need to add this element in my map nd. So I iterate over all the divisor. So for every divisor, for every m, I can say in my this is a divisor array. So div of arr of I. For every multiple, just simply say nd of m. It is equals to arr of I, right? So basically, this is a multiple. This m is a multiple, and for this multiple, we have we have this element, this divisor, right? So that basically I have added the information from I to the last index. So before processing the index I minus 1, I have the information from I to n minus 1. So in this way, we can solve the problem. If there is something which is not clear to you, then you can rewatch the recording of the session. But what I would suggest is just go and dry run for one or two examples. Everything definitely makes sense to you. Please tell it's a monotonic stack pattern or not. So this problem cannot be solved with the help of a monotonic, because lot of numbers are divisible by arr of I. So what I'm trying to say, arr of I, arr of I has a lot of a multiple, that is ARR of I itself, then a 2 into ARR of I, then a 3 into ARR of I. So how you can find the next divisible? Because basically in a monotonic stack, what we generally do, we store the element in some particular order. This is what actually the property of a monotonic stack. So in monotonic stack, we store the element in some particular order, but in this problem we have to check for the divisibility. So how you can store the element in a particular order? So just to mark this pattern, that in all the monotonic stack or monotonic queue problem, we store the element in some particular order, that is either increasing order or a decreasing order. So that's why this problem cannot be solved with the help of a monotonic stack. I'm not 100% sure, but if you have some solution which is with the help of a monotonic stack, then that is really great. Just make sure to post your solution in the comment box. But I don't think there exists any monotonic solution for this problem, because the general idea for the monotonic stack is to store the element in a sorted order, in some particular order, that is maybe increasing order, or maybe strictly increasing, decreasing, or strictly decreasing, depending on the problem statement. But here we need to check for the divisibility. So I cannot store the element in any particular order. It is not possible. So that's why let's go for the implementation. And yes, here we have the implementation. So this is my divisible 2D array. You can also use a map as per my implementation. So I don't have to iterate over 10 power 5. So I only need to iterate till the maximum element. So find the maximum element of the array, iterate over all the integer, then simply all its a multiple, and for every multiple, just simply add this integer I in a vector. The size of this map would be not more than maximum element multiplied by 128. Then iterate over all the integer from n minus 1 to 0. And if this key is present in my map, then the value corresponding to it will be my answer. Then update this element in your next divisible map. Iterate over all the integer. All it's a multiple. So this e is basically a multiple. And for every multiple, store the value AR of I. Just simply overwrite the existing values. Now coming to the example, coming to the problem, third problem. Make all 0. This is also I can say an easy problem, which can be solved with some basic observation, which is moreover like general reasoning, I can say. Anyway, so the problem is named as a make all 0. So in this problem, two players are playing a game involving energy stack. Each stack contains a certain number of energy crystal represented as integer in an array ARR. Player takes a turn. On each turn, a player must remove one entire stack, that is one element from the array. In each operation, a person can remove the element from the array. As simple as that. However, there is a special rule. If the bitwise XOR of the entire array is 0 before the player's turn, then the player will win the game instantly. And if it is not 0, then a player must have to remove one element from the array. And the game continues until someone wins, either due to the XOR rule or because the other player cannot make a move. That is when you remove all the elements from the array. And both the players play optimally, which is self understood. and you need to determine who will win the game for each initial array of the stack, and return true if the second player win the game. And generally we need to return true if the first player win the game, the person who start the game. But I can say this is one more extra thing, but not a problem for us. So return true if the second problem, if the second player win the game, otherwise return false, right? So coming to the first example, here the initial XOR of all the element is a 0. So the first person will win the game. He don't have to perform any move, and we have to return false because the second player has lost the game. Now let me explain you this example. Yes, Hemant, this problem was comparatively easier than the second problem. So 1, 2, and 4. So let's find the initial XOR. So let's call this as XOR sum. Not exact. Using the word sum here is not like not appropriate at all. But in my implementation also I use the sum. I use the name of a variable as a XOR sum. So that's why let's keep this as a XOR sum. So one, that it will simply store the XOR of all the element. 1 XOR 2 XOR 4. So let's find the XOR value. So the binary representation of 1, it is leading 0 and then 1. Then for 2, 1 0, and for 4, 1 0 0. Right? So the XOR value would be 7. So we all know the basic funda of XOR. If the number of bits are even, then the bit would be set in result. Otherwise, if the number of bits are even, then that bit is not active in my result. And if the number of bits are odd, then the result have the bit active at that particular position. So here in this case it is 1, and here also it is 1. Cool. So the XOR value will be 7. It is non-zero. So what the first person can do? The first person can remove any of the element. So just for the sake of simplicity, let's remove the element 4. So this is my initial array. 1, 2, and 4. Now let's say the first person has decided to remove the element 4. Now we are left with the 1 and 2, and the XOR value is still not 0. So the second person also have to remove the element. So let's say the second person has decided to remove the element 1. Then this would be my resulting array. And now the player first will play a move, and it is the player is restricted to remove the remaining element of the array, and now the array is empty. So the empty array has a XOR value 0, or I can say now it has a XOR value 0. So in this case, the person will win the game, the second person. So my answer will be true. So in this case, my answer is equals to true. So let me just quickly go through the explanation. So you can find any other configuration, but all the possibility, the second person will win the game. So the player 1 will remove element 1 from the array on his turn. Then the player 2 remove element 2 from the array, and now we are left with only one element 4. Then the player 1 will remove element from 4 from the array, and now the array is empty, which has the XOR value equals to 0. So that's why the player 2 will win the game, and we simply return true in this case. And then here we have the standard constraint. The value of n can be up to 10 power 5 and the element value can be up to 10 power 8. So let's draw some observation. And this problem was totally based on observation. You need to find the strategy and do some casework. I couldn't solve in a meantime, but solved right after constant. Okay, not an issue at all. But so ARR. So what I can say, instead of writing this way, let's consider the value of n. It is equals to 5, and the 5 element a1, a2, a3, a4, and a of 5. So let's first find the XOR value of each element. Basically the total XOR. So let's call this as a XOR sum. So this would be A1 XOR A2 XOR A3 XOR A4 and XOR A5. Now let's divide this into two possible cases. So the case 1. So the case 1, when the XOR sum is equals to 0. So if the initial XOR itself equals to 0, then the first person will win the game, right? So if the initial XOR is equals to 0, then the first person will win the game, player 1, and the second person will lose the game. And in that case, I need to return false. So I can claim my answer if it is a case 1. So if it is a case 1, then it is false. I know my answer. Now what if it is a case 2? So case 2, when the initial XOR is not equals to 0. So this will be my case 2. Now just tell me one thing. If you have a 5 element and the XOR value is not equals to 0, so what will happen in that case? What are the possibility you have? It might be possible when you remove some element and the XOR of an entire array becomes 0. So this is one possibility. In that case, and in that case, the current person will simply lose the game, right? So this is one possibility when the when the value of n is odd. So let's break this into two possible cases. So what if the value of n is odd? So if n mod 2, if it is equals to 1. So basically how I come to this approach. So basically I know the very basic thing, not exactly the basic, but a very interesting fact that if you have a even number of element, if you have a even number of element, and if you are given to remove two element from the array, then what you can do, you can make the same parity. If the XOR sum is non-zero, you can keep the element keep the XOR sum non-zero if you have a given the privilege to remove two element. So if you have a even number of element, if you have a even number of element, and if you have to remove two element from here, and if the entire XOR, if the XOR of this entire array is a non-zero, and if you can remove two element from here, and the XOR sum will remain non-zero. This is one basic observation. So if the number of elements is odd, so in that case the second person has the chance to win the game. The second person can win the game. So in that case, I will just simply return a true. So my answer will be true. Because what the person can do, here we have a 5 integer. What the person can do, person can remove the element. right? The person can remove the element, and now we are left with the even number of element, right? So there is only two possibility. The first possibility, when the entire XOR becomes 0. So if the entire XOR of the remaining array becomes 0, then the second person will win the game, right? Otherwise, the second person has a privilege to make the XOR value again non-zero, right? Because again, try to pay more attention. The first person, player 1, has removed one element, right? The player 1 has removed one element. Let's say it is A4. Now there will be two possibility. The XOR value of the remaining array is equal to 0. So in that case, the second person will win the game, right? And if the XOR value is not equal to 0, then second person can also remove some element. The second person can also remove some element such that the XOR value of the remaining array is still not equal to 0. And if it is not equal to 0, then we are left with the 3 element. Now the same thing goes for the first player. The first player again has a possibility, has a chance to remove one element. Now there will be two possibility. If the remaining array has XOR value 0, then the second person will win the game. And if the remaining array has a XOR value not equal not equal to 0, then what the second person can do, second person remove one more element. Let's say it is A5. The second person has removed one element A of 5, and this is 100% true. This is my claim that the XOR value would be non-zero, and here you can see we are left with only one element, and this one element is always positive. It is mentioned in the constraint that all the elements are positive, so the XOR value is not equal to 0. Now the person is restricted to remove this element, this leftover element. Now the array is empty and it is a player 2 chance, so player 2 move, so the second player will win the game. So this is my general strategy. If the value of n is odd, then the second player can win the game and we return true. And what if it is even? Else wala case. So if n mod 2, if it is equals to 0. So if it is equals to 0, then in that case, the player 1 has a strategy to win the game, so that the second player will lose the game, so we return false. I can give you the same argument for a even case. So let's say the value of n, it is equals to 6 and a of 6. So what are the possibilities we have? So we all know the entire XOR, initial XOR is non-zero, right? So what if I remove one element? So if the XOR of even number of elements is non-zero, then yes, it is possible. It is possible to remove one element such that the XOR value is still not 0, right? Because we all know if the XOR value is equals to 0, then we have all the elements the same. Because A XOR A, it is equals to A XOR 0, it is equals to A, and A XOR A, it is equals to 0. So when two elements are same, then their XOR value is equal to 0. In all the other cases, the XOR value would be non-zero, right? So if you have an even number of element with the non-zero XOR, then you must have one element which you can remove, and the XOR value is still non-zero. Right? So let's say we remove this A2. Now for the second person. For the second player, what the second player can do, second player can remove one element. So second player can remove one element. Let's say this is A of 5. So now there will be two possibility. If the XOR value is equal to 0, the first player will win the game immediately. And otherwise if it is non-zero, then second player, then again we have a even number of case. We have even number of elements. So I can give you the same argument that remove one element, the XOR value would be non-zero. Then the second player has the same option, remove an element. Either XOR becomes 0 or we are left with a two lesser number of elements. So if you remove two element in each couple of move, then the parity of number of element would be same. So this is my complete explanation. So XOR sum, take the XOR of all the element, and if it is 0, then case 1, return false. Otherwise, if the size is even, then return false. Player 1 has opportunity to win the game, otherwise return true. Now coming to the last problem of the contest, treasure teleport. So in this problem, you are given two array A and B of equal length. A of I simply represent the amount of treasure in the ith house. B of I, the destination index. From A of I, you can reach to index B of I. From index I, you can reach to index B of I. You can take a jump. So the destination index, if you use a teleporter which is inside the ith house. So a thief start with the house 1. You need to consider one base indexing and can take any of the following action. So the action of type 1 and the action of type 2. So the action of type 1 simply says that the teleporter, that they simply use a teleporter to teleport to house with the index v of I. And after teleporting, the current ith house loses all its treasure. That is, element value becomes 0. The second type of action is steal from the current house, that is, consume the entire value a of I and make it equals to 0. Then the player move to the nearest house, nearest index j, such that the value is greater than 0. And from there he can again choose either to teleport or the steal, following the same rule. And we need to maximize the total treasure, total value that we can obtain, total sum that the thief can collect by choosing the best sequence of action. And initially the thief is at index 1, and the process continue until no more valid moves are available. Cool. So let me explain you this first example. And this is my array B 3, that is from index 1 you can reach to index 3. One base indexing you need to consider. And from index 2 you can reach to index 3, then 4, and then 1. Cool. So the person is standing at here initially. So what the person can do, the best sequence of action is to take a jump from index 1 to index 3, from this index 1 to index 3, and then from index 3 take a jump to index 4 because the b of 3 is simply equals to 4. So take a jump up at index 4, right? And basically I performed two subsequent action of type 1. Then from here, then at index 4, start consuming the element. So in your answer, start consuming the element. That is, take this element with the value 100 and make it 0. So 100 will be added in your answer. Now from here, whenever I use a operation of type 2, I need to again switch back to some index which is less than I, which is less than I, such that its value is non-zero. And whenever you use a operation of type 1, then element value will immediately become 0. So these two elements are 0, a of 1 and a of 3. We are left with only one non-zero element, which is a 20. So we simply make a transition to index 2, and yes, we redirect to this index 2, and from here we consume this element, right? So it is 100 plus 20, which is equals to 120. And here we have the same explanation. Now if you consider the second example, then each index will redirect to the same element 1. So same index 1. So it is only possible to consume one treasure with the value 1. So that's why the expected output is 1. Now let's draw some observations. But not exactly the observation. You need to consider this problem in terms of graph. And once you boil down the problem, once you visualize the problem as a graph, then you can just simply map the problem with a very standard algorithm, Dijkstra algorithm. And not exactly the Dijkstra algorithm, but I need to do some kind of modifications. Now let's visualize this problem. All you need to do is to visualize the problem as a graph. And then we can apply the modified Dijkstra algorithm. Cool. So what are the possibility we have? For every index, I have two possibility. Either consume the element or use a teleporter. So if I use a teleporter, then I will be redirected to the index b of I. This is one possibility. And if I start consuming the element, then I will be redirect to some integer which is less than I and having value non-zero. So what I can say? I can say index j such that a of j is greater than 0, right? So this is the case when I use a teleporter, and this is the case when I consume the element. So with this observation, let's try to apply the Dijkstra algorithm. So before applying the Dijkstra algorithm, what is my main agenda? So let's say the value of n, it is equals to 7. So we have array A, then A1, A2, A of 3, A of 4, A of 5, A of 6, and A of 7. So the very first thing, I need to know how many element we lost to reach at index I. This is the information that I need to keep track. Yes, it is possible. It might be possible when it is impossible to reach at index I. So in that case, we use some other representation. But just for a sake of simplicity, let's declare an array of size n, and let's name this array as lost. So lost of I will simply store minimum minimum loss that we need to bear to reach at index I. So minimum element, or I can say, yeah, minimum elements sum that we need to lost to reach at index I. So what will be my answer? So if I decided to end the journey at index I only, then what will be my answer? My answer will be prefix the sum of I, right? So let me just quickly write in this way. So that would be equals to all the elements are till index I. So A1 plus A2 plus A of 3 plus up to A of I and minus lost of I, because lost of I already stored the losses that we need to bear. So lost of I. Now, one very common thing that comes to everyone mind, that it might be possible when we take a jump beyond index I, and then again we come back to index I. This is a very popular. This is a very common sense that we can use. So now you might ask that, hey Ayush, it might be possible when from A1 we reach to index this A of 3, and then we lost A1 and A of 3 both, and then again we just simply teleport to index 7, and then from index 7 we again teleport to A of 4. So what I'm trying to say, you don't have to consider anything which is beyond index 4. This is my index I. You don't have to consider anything which is beyond index 4, because at this point of time I decided to make a claim that my destination journey will end at index 4. So how many lost that I need to bear? So it is nothing but the sum of all the integer from 1 to index I, and the element sum which we have lost. So it is basically this A1 plus A3 has already stored in lost of I. So you don't need to worry about this thing. And if you are coming via some index which is greater than I, then we also consider all those indexes. Also, we also consider lost of 7, we also consider lost of 6 and the lost of 5, and whichever give me the best result, I will select that index as my destination index, where we end the journey. So you don't need to worry about this thing. So my overall answer will be, so let's call this as a current answer. So this is my current answer, and my final overall answer will be, I iterate over all the indexes from 0 to n minus 1, and this is nothing but the prefix sum. So prefix the sum of I minus lost of I for all the I in the range from 1 to n minus 1, right? Now the thing is how we pre-compute this lost of I. So for this thing, for this lost of I, what you can do, you can just simply apply the Dijkstra algorithm. So apply the Dijkstra algorithm. Now how we apply the Dijkstra algorithm? So you declare a min heap, right? Because to maximize the current answer, this is constant. To maximize the current answer, the prefix sum is constant. All I need to do is to maximize the loss. Maximize the loss for a to reach an index I, right? And to sorry to minimize the loss. So we want to minimize the loss to reach an index I, and to minimize the loss, we can use simply apply a Dijkstra algorithm, right? So declare a min heap, a very trivial step of a Dijkstra algorithm. Declare a min heap, and this min heap will simply store a pair. It will simply store a pair of two element, and initially it is 0 comma 0. So now this first element, this first element will store a lost, and the second element will simply store the index. So basically, to reach an index I need I need to bear this much loss, right? And going to initialize all the losses with the -1. So if it is a -1, then it is a first visit to index, and simply update the loss. So declare an array lost, and it would be of size n, and initialize all the element with the -1, right? Because initially I do not know the answer for any index, and this is my initial condition. So basically in my implementation I converted everything to a one base indexing, but you can also use a everything to a zero base indexing, but you can also use a one base indexing. This is totally up to you. Hi Vishwajit. So after this, simply apply the Dijkstra algorithm. So run Dijkstra. So rest everything is implementation, how smartly you can implement this thing. Now coming to the implementation, everything will explain during implementation. So here I use a macro, that is convert every integer to a long just to avoid the overflow case. Now this is the method. This is the method that you need to complete. Max a treasure. Taken the size of the array. This is my loss array. Initialize all the element with the -1. This is my min heap, that is a min priority queue, and initialize this with the 0 comma 0. So I'm assuming that we are coming via some imaginary index, and to reach at that imaginary index, basically we are coming via some imaginary index with the loss 0. Loss value is equals to 0. Then simply run a directional algorithm while the size of the priority queue is greater than 0. Then remove the element with the minimum loss, and this is the value of loss, and this is the index value, and remove this from the priority queue. And if you already calculated the result for this index, then simply skip this index, because and as much as we try to minimize the loss as much as possible. So if you consider more elements, then your loss will be maximized, and if you maximize the loss, then overall current answer will be minimum. So that's why if I already know the result, then I know it was the best one. It was the best one which I got earlier. So skip this index. Otherwise, otherwise this loss of I will be equals to D. And then in my priority queue, I had two possibility. That is this is the possibility when I use a when we simply consume the index I. So if I consume the index I, sorry, yeah, if I consume the index I, then this will be my total loss, right? So if I consume, so d plus a of I and comma b of I minus 1, that is take me to this index, right? And if I use a teleporter, then make sure that index value must be, sorry, This is the case when I use a teleporter. So this is the case when I use a teleporter. So in that case, I will lose the value which is at this index. So d plus a of I, and this is the case when I consume. So when I consume the element, then then the lost will be as it is, and take me to the index I minus one. Now some of you might ask that, hey Ayush, how you would claim that we have to reach at index I minus one? So actually you don't need to worry about this thing. If the element value changes to 0, then also we check both the possibility for that index, right? So that's why we can just simply take a jump to index I minus 1, because eventually we are only interested to consider the lost. We don't have to consider the leftover value that we have. So after this, initialize the answer with 0, and this sum is basically my prefix sum till index I, and it is initially 0. Then add the current element, and if loss of I is a not equals to minus 1, then this simply means index I is reachable. So update the answer, prefix sum minus loss of I, and finally I'm going to return this answer. The time complexity would be n log of n base 2. Why you don't explain in Java? So actually, Vishwajit, it is not possible to discuss the implementation in all the three languages. But now we have such a powerful AI model, and you can go and just simply convert this into a Java, which is not a big issue. I can say. So yeah, that's all from my end for the today's session, and hope you have learned something new. And make sure to write your comment in the comment box. Will definitely improve the upcoming session and upcoming problem set. If you faced any issue with the explanation or the problem. So thank you everyone for joining this stream or watching this video, and have a great day. Good night ahead. Bye bye.